we have successfully completed this part. Okay, so next part, what I'm going to do is, we already have state machine, we have Cartesian trash, joint trash. We're going to do joint control and then use MJ step, which is the dynamics. So I need to set it in a mode where I can do joint control. Now, before we do that, what I need to do is, there are two things. What I'm going to do is, I'm going to make I have to change the XML file. I'll tell you what I need to do for the XML file. So right now, if you look at the XML file for the robot, it's set to do position control, and it's clear over here. So you can see it's position control. I want to do basically torque control. Okay, I want to set the torques. So I'll change this. That's the first thing. So let's I'm going to just change this here. Stake position, and how do you replace this? Replace it with motor. So that's the keyword for replacing it with torque control, and then we don't want to do anything else. We also need to remove this class thing because it's not really there's no really class. The class is think of it like a variable which is defined earlier. We don't really want to use that. So get rid of this. And these things, you don't really need them. Let me just comment them. So we don't need that. I just want to run this, so I'm sure that the XML file I changed is not erroneous. If it runs fine, it doesn't do anything different. Okay, it's fine. Let's close this. So it works fine. I'm going to now decide to split this into two types of code. One is I'll create a flag. This is for trajectory generation, which I've already successfully done. Okay. When I set it to 1, I will basically run in the trajectory generation mode. When I set it to anything other than 1, I will execute the dynamics code. So let me go right here. All these 3 things are common. All these 4 things are common, actually. So let's do this. Equal to 1. Indent it, and else. This is dynamic mode. This is the kinematic mode. I need to do MJ step. Okay, so the result here is going to be that if I run this code now, when I set this to 0, is that the robot is going to fall, and nothing is going to happen because there's no controller right now. Okay, so what I need to do now is to set torque control. I would create a controller called joint control, and that would have no input arguments. So let's create this function. Okay, now when we're doing joint control, remember that this is running a state machine. Just to recap what a state machine is, we have different states, FSM stand, swing, stance, and so on. And we might want to do different sort of joint control in different phases. So in FSM stand, we can just maybe get done with PD control. Swing, when it's moving in the air, we can just do PD control. But stance, when it's applying a force against the ground, when the foot on the ground, we might want to do something else. So I will basically write different, basically do the joint control depending on which state the robot is. So let's do that. Let's go here and say if, well, we need to run this for each and every joint. So the first thing I do, just like what I've done in all cases, is I will run a loop for all the legs. So let's run a loop. And here we would put if, it's essentially the same thing. So I'll just copy it just to save time. So if this is in FSM stand, then I need to do something now. I need to get these variables from global. So just to save time, let me just pick this up from here. So this is in globals. These variables are in parameters. So let's get those. So we have everything available here. Now, what I'm going to do is I'm just going to program a simple PD control. Simple PD control. Okay, so PD control would look something like this. Torque equals minus Kp times Q. I'll call that Q, well, let's call it Q actual minus, we already have defined a variable for the reference. If you go to globals, you'll see that we've already defined qref, uref, so we need to use that. So let's say qref, and then kd times, this will be the velocity, so u act minus uref. Okay, so I've already defined qref and uref. I have not defined qact, uact. These are the actual values. So let me create global variables that we want to can make this more efficient. So let's define, this is joint control. This is just saying what variables are called in what. So q, so let's define global, qact, uact. So I believe that you don't really need global here. You can check it out. It's just that I put it there. So let me just continue doing that. But the code should run fine without global, I think. So qact, uact should have the same size as this. So these are the joint angles, and there are 12 joints. And 12, of course, 12 velocities. So where we do this, this is basically coming from the state of the system. The state of the system is stored in here. So let me go. A problem saving, I think it's fine. So let's go to all the way here. And right before joint control is called, I would like to get qact. That should be saved in qpose. Now remember, qpose runs from, qpose is the state. If you go to the state variables, which are, see if I can get this. Yeah, so the states, there are 7 free variables, and then you get basically the joint angles for the legs. So I need to start the index from, well, 7 free, so it'll go from 0 to 6, and then 7 onwards would be qact. So let's figure that out. Let's get that in code. So this would be 6 to rest, and I'll just do copy. And then uact would be in data.qpose. Now this will be slightly different. That's because there are 7 states, because there's a quaternion which has 4 numbers, and this one has 6 numbers. So I need to start numbering from, so 0 to 5 is velocities for the trunk, or this part, and then I need to go from 6 onwards. Sorry, 5 onwards. So this will just modify slightly. It will be I think this is wrong. This should be 6. I did a mistake, I think. This should be, it will be 7, because 0 all the way through 6 is, so 0 to 6 is 7 numbers, these are the 7 positions, and then this should be velocity. Okay, just confirm this. Yeah, that should be right. Okay, so now I have these variables. Now what remains is that, well, I should call this globals, otherwise it won't get updated. Okay, now I need to go in joint control and do this. Now this is running a loop for all 3, well, it's running for each leg. Each leg has 3 degrees of freedom. So that is the roll pitch for the hip, and then the knee joint. So I need to have three things here. So let me call that, let's save this in a variable called torque. This torque variable will basically keep track of all the torques. And since I will just deal with global values because this will be somehow mapped to the torques here, I'm just going to create another global variable called torque. In fact, it just saves me time if I just do trq and add this here, and then I just do, it's again will be 12 numbers for the three variables. Okay, so that's that. Let's go here. Now I need to do globals dot trq, and remember this is indexed by leg number. So the way I can do this is 3 times leg number equals sum kp times just think if it might be easier if I guess I was just trying to see if I can define it here. It's never mind. Let me just, this will actually be very lengthy. Let me just do this. This will make our life easy. Globals dot q act. U act is globals dot q act. So this is, these variables will be short. Q ref equals globals dot q ref. And then uref is globals dot uref. So now it's kind of easy for me to just put the same thing. Okay, so kp is something I need to give. I always like to give some value, like just put 10, and you can either do 10% of that. In this case, I figured out that 10% is actually unstable. Well, you can try and put, so 10% of 10, just start value. We have to now also give the leg index. So this would be okay, so what happens here is if you put leg number equal to 0, you get 0, 1, and 2. If you put leg number equals 1, remember the numbering starts 0, 1, 2, then there'll be 3, you should get 3. So if you put 3, 4, 5, that will be the next leg and so on. So this actually logic works. Now this is just doing a PD control in FSM stand. So in order to test this out, what we have to do is a couple of things. We'll go here, and once you run joint control, it'll actually assign global.torque. This has to be assigned back to the appropriate variable in MuJoCo. So that would be data.ctrl equals dot copy. This will work. Okay, so this is this. And then what we want to do is I'm going to just do one thing here in state machine. The state machine just transitions from state machine transitions back and forth in stance and swing. I'm just going to stop it from transitioning from the stand phase, the first phase, so I can check the coding for that. So here, let's open state machine, and we're just going to halt this, halt these things. So what we do is we can just comment out this. So it prevents this transition. So it'll just hold on to it's just hold on to the stand. Let's see if this works. We have too many things here. I'm going to close a few things. I need state machine. I think I don't need this. Okay, so let's see what happens now. Let's run this. Okay, I think that the gain is not big enough. Let's ramp up the gain and see what happens. So the way I like to do this is let's call a gain parameter. So let's run this and see what happens. Okay. It seems like it's transitioning. It's going back and forth. Hold on. Let me just totally get rid of these things here. Let me not transition. So let's comment out this whole thing. But then I think this will give you an error. See, what's a good way to do this? I can do pass. Yeah, so pass is one way. Otherwise, I was thinking of just saying going to state machine and then just chopping it off from the call here. That also this also work. Okay, so this is there's some transition going on, but here it is. So here we got the robot to stand. It's not transitioning, it's just checking. We're just checking this part of the code. So this looks good. Okay, now we can go to the next part, which is now we've already programmed the movements. We just have to get the controller to work, which is what we need to do is go to state machine and uncomment this out. So it does transition. Okay, and what we're missing here is that in joint control, we want to essentially do something similar for swing and stance. So good thing is the same code will transfer. This should go back, and this should be stance. This should be swing. Okay, let's see what happens now. Let's run this. So it's now a transition. It is doing what we expect it to do, which is move the legs in unison, but you can see that it's tilting the body. One of the reasons why it's tilting the body is because we don't have good force control. We need to do some kind of force control because at least in the stance phase, when the foot is on the ground, because when the foot is on the ground, it has to resist gravity, the feet, hold on to the pelvis. And so that's missing. So let's see, I'll show you a simple way to do this, and then we'll do it a more fancier way, which will take care of the vibration. So what we need to do is when it's in swing phase, I'm just not going to bother with the swing phase. The leg is in the air and the legs are lightweight. So I really don't want to do any fancy control here. By fancy, I mean gravity compensation. But I do want to do gravity compensation in the stance phase. So I need to add a gravity torque here. So my goal is to add a gravity torque. It's called 0. Gravity 1 and TRQ gravity 2. Okay, so I'm going to use a rather simple technique of doing this. So here's what I'm going to do. Okay, so first we'll do simple gravity compensation in stance. Okay, so this is the robot as a box. It has 4 4 legs, and the 2 legs are making contact with the ground. So this is in the air, this one is in the air. So we can see that this is making contact, this is making contact. This has a mass and a gravity, which is acting downwards. And the feet are massless. So feet are massless. So feet are massless. We're actually going to make M as mass of, I think it's called trunk, plus M of all legs. So we're going to do, we're going to assume feet are massless, but assume that all mass, so 4 times, this should be 4 times M legs. All mass is lumped in the trunk. Okay, so this M here is going to have all the mass of the robot. Now, what we're going to do is we're going to assume that there is some reaction force, in this case, Fz. Okay, and then there's Fx and Fy, which are essentially 0. So Fz, Fx, and Fy. Okay, and so we're going to assume that if you do a simple force equilibrium in the z direction, you get Fz plus Fz, just because you assume that both legs take the same weight. Equal to mg, right? So Fz is 0.5 mg. And then, of course, if you do force equilibrium in x and force equilibrium in y, you will get essentially 0, right? So the force of force due to gravity is F equals 0, 0, 0.5 mg. So this is each leg. Now, this force has to be translated to a corresponding torque on the leg, because we can't talk in terms of force. So what we do here is, if we have the leg and then there is the force, then in order to compute the torque, we have to just do minus Jacobian of the torque times F leg. And this is the gravity torque. That's it. So we've seen how this works. This is a derivation I did some time back on how to use the torque to transfer the forces from the end effector, which is, in this case, the end effector is the foot, to the torques on the joints. So this is pretty much what we'll do. Okay, so let's see what happens if this makes the code any better. So we go here. We've already, so in stance, we have F equals np dot array. Now I need to have 0, 0, 0.5. I would actually define, so I actually did the calculation to figure out what the mass is. So the mass is about 12.453. Let me just put this in parameters. So here we have parameters. The mass is 12.453. Gravity is 9.81. So then I can pull it up here and say params dot mass times params dot gravity. So it's ready, but I need to compute the Jacobian J. And for that, I already have something ready. I did this, if you remember, some time back. We did for homework, I think it was homework 7. We had this particular question for the homework. We need to compute the Jacobian. So we have this Jacobian for the leg available with us. This is a code I have over here in, it's be called Jacobian end effector leg. Let me show you what it looks like. Okay, so I need to send in the joint angles, and I need to give the leg number, and it will basically send me the Jacobian for the it send me the linear Jacobian, not the angular one. I need the linear one only because the force F on the system is a linear force, Fx, Fy, Fz. It's not Mx, My, Mz. If there was Mx, My, Mz, I'll have to use j omega. So all I do now is import this function. No, sorry, it's this one. From this, import that, and let's use it now. Okay, so leg number is fine. Q has not been defined. Let me define Q. Q would be np.array. It will be essentially Q. Okay, now we have a choice. You could use reference or actual. It's always recommended to use reference because reference value is less noisy. So I'll use the reference value. So all I need to do is take this. So it will be the successive joint angles. So +1, +2. So this is now being used to compute. Actually, you know what? Let me write this Q leg. That way it's super clear that it is not anything else but just for the leg. And then let's compute TRQ gravity equals minus J dot transpose times what did I say? Fx, Fy, Fz, so F. Okay. First, before we compare this, I'm going to best make np dot zeros. So this is just so that we can compare the two. Let's put zeros first. This was our original simulation. So let's run this, and you'll see it's the legs wobble. Well, not the legs, but the body wobbles. Okay, now let's turn this on and see what happens. It's much better. It doesn't wobble as much. So the gravity compensation helps. It's still doing something which is, it's actually, if you see carefully, the body is going back and forth. Okay, so we've achieved some sort of force control, sort of good trot control in place. Let's do the next step, which is we'll get the robot to walk forward now. Okay, so a state machine was only setting LZ and LZ, which is basically movement up and down. Let's set movement in the fore-aft direction, so front back. Okay, so for that, what we need to do is so we'll work with state machine now. And set LX I and LX F. So when the robot is, a side view is best because it's moving front back. When the robot is going front, its legs would be something like this. Okay, this will be the start when this foot is on the ground. And then when it is moved forward like this, the leg will go back. In other words, this is going to be front, and it's going to be back with respect to the tip, with respect to this point. Okay, so if we specify a velocity for the robot, let's call it x dot ref. We know the distance covered, so let's call this, it's going to be symmetric. Let's call this distance as Lx, same Lx. So here Lx is going to be x dot ref, okay, times t step, because that's the time it takes to do one step. So velocity times t step, but remember it's going to be half of that, right? Because it covers half over here, half over there. So it starts off with, this direction is positive. It starts off, this is Lxi, this is Lxf. It starts off with a positive value because the foot is going to be in front. It ends up with a negative value, which is minus 0.5 x dot ref times t step. So all I need to do is put this in the state machine, and then the IK will take care of figuring out what interpolation is. So this is in the state machine. Then in the Cartesian traj, I will need to get Lx ref, which basically comes from the, it'll give me Lx dot ref, which is the velocity, which will come from quintic polynomial. Okay, so that's the logic. Let me save some time. I'm going to just take my copy paste from my code, which actually does that. There are few things you need to do. You need to ensure that globals have, we have defined this. We actually have already done the work of defining all these variables. So we're good to start with state machine. So in state machine, I've only defined LZI, LZF. I need to define LXI, LXF. So let me just copy paste it just to save time. So it should be, okay, so we are going to transition from, we're going to look the stance one, not here, sorry, should be here. So we are transitioning from swing to stance. In stance, when you're in stance, I said that we will be forward and then we'll go backwards, or the relative foot would be, with respect to this red dot, would be front to start and be back. So all I need to do is right here in stance, when it switches to stance, I should have this. So positive, negative. I don't think I've defined x dot ref, but we can define that. So let's define x dot ref in, well, before we define that, we need to do exactly the reverse for the swing leg. This is the stance leg. The swing leg will be doing exactly opposite. It will start off forward and go backwards. So just know, you can reason it out exactly like I reasoned out here. So I'm just going to take this code and copy paste it in swing, but I'll reverse the sign. Okay, so this would be negative, and this would be positive. And I also, as I said, x dot ref is not defined. I need to go in globals and define it. And default, let's define it as 0. So going back here, running this code just to ensure that I did not make any mistakes. So it looks fine, but it's not moving forward. So I need to make it move forward. Now I'm going to have another piece of code which I pre-wrote, which basically does the forward movement. It is set command step, and I'll tell you what it does. Okay, so what this does is, when you're trying to control the robot, you want to set the speed, but you don't want to set the speed. You want to change the speed every step versus changing it every instant of time, because what does it mean to change the step at this very instant? Let's say it is, at this tick it is 0.1, and the next tick you make it 0.2. That's going to not really work out very well, at least the way I've coded it. So I'm going to just make this change in velocity be every step. So for that, what I do is I specify, in this particular function, if I specify the desired velocity or desired command, I give it the current command, it'll actually use the min and max and rate to figure out how to advance this. So it might be a little confusing right now, but let me get back to this in just a bit. To for this function to work, I need to basically keep track of the steps, which I'll do first, and then I'll come to this file. So what I'm going to do is I'm going to keep a track of step. I actually need to keep a track of the previous step and the current step, and I'll set the previous step. Won't let me escape. Go to 1 sec. Hide video panel and hide. What, while I'm here, let me, I don't think I turned this on. Okay. And hide floating. Yeah, okay. So I'm going to initialize them to 0. Okay, I need to keep track of steps. So what I'll do is I will go in state machine, which basically is the engine which keeps track of, I don't need these things, too many things over here. Okay, so what I'm going to do is I'm going to keep track of the state of the steps here, right here. So every time I switch, remember that both this loop is run for all the 4 legs. I just need to switch when either of those legs make contact with the ground, right? The 0 or the 3rd leg or the 1st or 2nd leg. So I'll just run the counter for one of those 2 legs touching the ground. So when the 0th leg makes contact, the step is incremented by 1, or the 1st leg makes contact. There's no point in doing it for 3 and 2 and 3 because 0 and 2 work together. So I'll increment the step, and now I'm going to write a additional code which will actually get this in motion. Let me close this. I don't need this. I don't need this. So I'm going to write a function called high level control, and this the role of this high level control is to just increment the velocity. That's all it will do. Okay, so let's from high level control import high level control. Let's make a new file, Python file, def high level control. So high level control dot py, and the logic for this is that it will only increment the velocity if at all it sees that the step number has increased. So what I'm going to do is I'm going to import, as always, I have to import few things every single time. So these things have to be there. And what I'm going to do is if globals dot previous step is less than globals dot step, then globals dot previous step equal to globals dot step. So what this is doing is, remember that both these variables set to each other 0, 0, but when it goes into state machine, when the foot hits the ground, you increment the step number, so it becomes 1. So the moment the step number becomes 1, this code looks at that. So it says 0 less than 1. So it sets previous step to 1, which means that this loop runs only once per step. That's precisely what I want. I need to increment my commands or the velocity every step. So what I'm going to do now is the actual part where I'm going to increment will come now. Here is how to use the function step command, which I talked about. Okay, so what I do is I take the current velocity, which by the way is 0. I want to go to a speed of 1 meters per second. Okay, so the input to this set command step, which I should import, let me import that from set command, step, import, step, command, step. So what it does, it takes the desired value. I want to go to 1 meters per second. My current velocity is 0. And it actually outputs the velocity, but it uses a few things to output the velocity. It looks at the minimum and the maximum velocity. So if it is exceeding the minimum or maximum, or less than minimum or greater than maximum, it will not increment the value. And it also looks at how fast you want to increment. So if you want to go from 0 to 1 in one step, it will not do that. It will look at this parameter dvx. So I need to set these parameters in my, and then self.dvx. So this is how fast you want to increment. I'm just going to randomly put 0.1. So it can only increment the speed by 1.1 meters per second every step. So if you try to do 0 to 1, it'll take 10 steps to get to 1 meters per second. That is just to prevent it from doing crazy things. Okay, so right now, this code, I think, will run. It'll try to get the robot to go to 1 meters per second in whatever time, depending on dvx.
So in the terminal, where it has those three, right,
yes.
exit, and then parentheses, parentheses.
Okay. Oh, I see. Okay.
Now you can run the code, and then you do have a bug in high level control. You imported step command step instead of set command step.
Thanks. Okay. I hope this will run. Thanks a lot, Daniel. Okay, let's see if this runs. Okay. There's Steph reference. Okay, so this is a problem with globals. I should do globals.step. Okay, so it's doing nothing. It's because I had not actually completed my code. So state machine does it, but I really need to put this in here. I forgot to do that. So I had commented this out. Now it is setting the velocity in the forward direction. Okay, so it's not doing anything. First thing to check is it's actually, okay, did I not call high level? I think I called high level. I did call, in fact, I can check print globals dot so this should increment every step. Point. Okay, so it's incrementing, but it's not going forward. So let's see, it's probably somewhere. I don't need this. Let me see Cartesian trash. I'm actually incrementing that. Am I not interpolating? I'm not interpolating. So there's no LX ref and there's no LX.ref. So I need to add that to the code. Okay, so this is as simple as taking this and then just here, LX and this should be, shouldn't be half. Half was specifically for LZ. Okay, let's see if this works. Okay, it's a bit slow, but yeah, it's going forward. In fact, it's not very stable, you can see. Okay, I'm going to stop this. There's something you can do. It goes out of view. We can fix that very quickly. I'm going to make the robot, the camera move in front. The way to do this is to, here there is this cam.lookAt. That basically is where the camera is looking at. So what I'm going to do is I'm going to just say that cam.lookAt0, which is the X position of the camera, should look at the X position of the robot, and then cam.lookAt for 1 should be data.qpose1. Okay, so it starts moving forward, and you can see the camera is also moving, so the robot is already in middle in the view. But this is not very stable. It's not what you would expect it to do, right? It's shaking. Okay, so we'll fix that in just a bit. Okay, so now to test this, what I'm going to do is go back to high level control, not set the velocity, so just keep it 0, but we'll modify the y velocity. So I'm going to set the velocity from 0 to 0.4. Let's see how this pans out. Let's run this. We need this view. You can see it's actually going to the right. It's struggling, but it's going to the right. So we sort of got the basic motion there, but it's still struggling. In fact, you can see that the roll, it's rolling back and forth. It shouldn't be doing that. The trunk is not perfectly flat. So we'll fix